We might make a start. Thank you. Welcome to members and guests to our social evening for August. And also a special welcome to Dr Warren Hankey from UTAS, who's our presenter tonight. A little bit more about Warren a bit later. Just a few catching up on news. We've had a very busy August with Beaker Street. We've had some very successful evenings under the sky at both Bellarive and Hobart waterfronts. So I've collected some very rough numbers for those nights, and well over 500 people have come up to our telescopes over that time, which is a tremendous effort. And it was great to see all our volunteers engaging with the passers-by, giving them a connection to the night sky, and just their enthusiasm helped, I'm sure, win a lot of people over to getting connected with the night sky. And a big thank you to the volunteers, and also to Michael Booth, who coordinated the events. We had a group up in the northwest that were all due to do a sidewalk astronomy evening. Unfortunately, the weather got in the way there, but they're starting to roll up there as well, which is great. We've got lucky draw prizes tonight. We have Southern Nights about Aurora. Photographers Benjamin Aldridge, Paul Holan, Andrew Phipps and Luke Sharkey. And that prize is kindly donated by Lisa, so thank you, Lisa. There's a Beaker Street beanie, or there's two actually, so two beanies to be won, and some cable management for some for other people get tied up in cables. Yeah, that's only a small start for you, I think. And if you miss out on a Beaker Street beanie, we've got AST beanies for sale, $25, and we accept card payments. Just send an email out, but just if you missed that email, that all the accommodation for Font Hill has now been fully booked. The Southern Dinner for Christmas, taking bookings, the QR code is there, so that's the Telegraph Hotel, 14th of November. If you're not sure whether you can make it or not, still register, and we'll keep in touch with you leading up to the event. There is heaps of reading, Sky and Telescope, etc., in the yellow bin over near Matt, so please help yourself to a copy of Sky and Telescope. So we had the Messier Galactic Bulge Challenge. So people have been fairly shy or not forthcoming in their in their efforts on that, but I've heard from quite a few people they enjoyed doing it. One person sent their observation sheet. So if you haven't sent your observation sheet, and when you see this certificate, you'll want one as well. But I'd like Steve Harvey to come forward, please. So, congratulations, Steve. So Steve, obviously, yeah, he got all 30 objects, and I did too, but I can't present myself with a certificate. Yeah, terrific. Well done, Steve. So yeah, as I said, if you've been shy, look, if you haven't had a go at it, just send me your observation sheet, and I'll organise a certificate for you. So at the conclusion of Warren's presentation, tea and coffee, and that'll be followed by our very own Richard Grudzien's presentation of what to look out for in September's night sky. So thanks, Richard. I know you put a lot of work into those presentations. You got a you got. I did give you an accolade earlier, Michael. You missed it. Tempting. No, well, thanks, Michael, for your organisation and coordination of the Beaker Street events. Thank you. Well done. Amazing. So this week's special guest speaker is Dr Warren Hankey. So AST has a lot of friends, but no better friend than Warren. He's there when we need him. It's lovely seeing him and his dog walking around and keeping in touch with us. And you know, events like our open night would not be the success without Warren's assistance. So it's really terrific to have you here tonight for your presentation. So Warren will be discussing the radio telescope facilities at UTAS. Is it 7 radio telescopes? Now,
I added them up, 7, I think.
7? Yeah, don't lose any.
Last count, I know.
So I guess for us, the dishes are like the sentinels that are watching over us while we're looking in the night sky. So it's really comforting to have those dishes there, and we really feel like we're astronomers when we see them. Warren's going to take us on journeys, spacecraft tracking, Geodesy.
Geodesy.
Yep. National and global collaborations. So people logging in to the system from all over the world. Pulsars and Quasars. So, welcome, Warren, and we're all looking forward to your presentation.
Yeah. Okay. No, thanks. Thank you. Yeah, I've got a few notes here because I can't remember all this stuff. What we're looking at there, so I'm going to talk tonight about what our radio telescopes do, our facilities. I think we've got 7, last count. And what it is we do up there. And one of the principal things we do is international and Australian collaborations, radio telescopes all around the world look at the same thing at the same time. We were doing that just today. And figuring out where Earth is in space, because all kinds of positioning systems need a reference point, and that reference frame is very distant galaxies. So they're practically at infinity, out at the edge of the universe, and so they don't move with respect to us. You can see the Earth wobbling around, radio telescopes moving around with respect to each other, the length of the day changing, Earth's crust bulging and tectonic plate movement are picked up, things like that. So, but the basis of all that technique is quasars. So, started off as QSOs, quasi-stellar objects, because they look like stars. So that's a quasar in the centre there. It's got some number. What is it? OPO 9625A. And apparently this is the 100,000th image taken by Hubble. So it's just, there's a quasar there. It looks just like a Milky Way star. And up above it is an elliptical galaxy. We can see heaps of other galaxies. That's an elliptical style galaxy there. Maybe that's a spiral. That looks a bit like a barred spiral to me, something like Magellanic Cloud. Various types of galaxies and things. But it turns out, this one turns out to be 9 billion light years away. So it's got a redshift of greater than a half. And that is an elliptical galaxy that's 7 billion light years away, just above it. Yeah, what else can I say about that one? Yeah. And so these were discovered in the 60s, basically. What have we got here? So here's a famous one, 3C273. The 3C stands for the third Cambridge catalogue, because Cambridge, along with Parkes, identified heaps of point source objects. In fact, Australian scientists in 1949, CSI radio scientists, found the first point source object. This one's a quasar, which it's only 2 billion light years away. That's still a lot. And that's what it looks like on an optical telescope. But you notice here it's got this jet is actually associated with it. That's an optical jet. So that's probably millions of light years, that jet. And here using a coronagraph, so if you're taking a picture of the sun and you want to see the million-degree corona surrounding the sun, I think that's an artifact from the coronagraph. They've blotted it out and you can see it's in an elliptical galaxy. So what's making it so bright is a supermassive black hole. And it's accreting What have I got here? What numbers have I got here? Yeah, so we can see the host galaxy. So in 1963, a guy called Martin Schmidt got a redshift to this thing of Z.158. So it's moving away, appears to be moving away at 15% light speed. But when you see those redshifts and those recession velocities, they're not really moving away from us. It's space getting bigger between all the galaxies. So if you were in the rest frame of that galaxy, it's not racing around at high speed or anything like that. It's just the space between us and them getting bigger. So it appears to be receding. If it was a Doppler shift, it would appear to be receding at, 15% light speed, which is, what does it say here, 50,000 kilometers a second. But, yeah, like I said here, it's space expanding, not. What else can we say about that one? What's this wide field camera, something like that? That's another Hubble image, that one. What have I got here? Yeah, so quasars. So I've got to thank David. He's one of our Ozscope team. He's doing some graphics for some presentations, so he lent me this one. And yeah, supermassive black hole. Of course, people wonder why black holes are so bright, like in that last image. It's not the black hole that's bright, it's the accretion disk around it. So it's matter. You think they're usually in the middle of galaxies, well, they are in the middle of galaxies, the supermassive ones. So stuff's been falling in for millions of years, and as you're falling, it's accelerating all the time, faster and faster, and heaps of it, millions of years, accelerating in, and it all collides with itself. It's moving at high velocity, forms an accretion disk around the black hole, and that's what's shining really bright. And the jets are often really bright. Stuff's falling in, but stuff can escape at the jets. Magnetic fields in the galaxy are getting pulled in with the material too, and they're getting twisted up by this accretion disk, and you get these sort of helical magnetic fields at the jets. I'm probably preaching to people who know what quasars are. But yeah, you get plasmas racing along those, accelerate along those magnetic fields at close to light speed. So this is a super zoom in. I think they can estimate how big these accretion disks are because of they see these objects varying. This one on the last one, I think it was. Yeah, the last one varies on scales of about a month. So they know that it must be a light month across for changes to occur, so they can estimate size of things by variability. About a light month across, whatever that is in. What else have I got here? What does it say? Yeah, so, and at that distance, the last one we're looking at, I'll skip back. That distance, the luminosity, that distance would be 10 trillion suns. So we've got about, a few 100 billion in the Milky Way. So that's a whole lot more, another 10 to the 6 more. That's the luminosity, but they estimate the mass of the black hole to be 100,000 to 1 billion solar masses. So it's in a very compact region, large mass, and yeah, super, super bright. So they were very surprised when he first got that redshift off to this thing of 2 billion light years because it's so bright. It looked like it was another star. Yeah, so how do they get the redshift? Hydrogen, our friend hydrogen. Especially in radio astronomy, hydrogen is the thing we love. It's usually, I think he was looking at this line, the Balmer beta line. And that's the alpha line. So if you're looking at the sun, you're probably using a H alpha filter or something like that. That's 656, I believe, isn't it? H alpha. And this one's about 480. And he saw that shifted over to about 600 when he got the spectra of that galaxy. This is a laboratory spectrum, so that's why it's so beautiful and clean. And this is the molecular stuff, and this is the atomic stuff. Yeah, there's all this. So this is when the electron transitions from 4 to 2 level in the atom. The Lyman series, when it drops down to level 1, in the atom, that's in the ultraviolet. So these are handy for optical astronomers, like so in the 60s. This was the line they were looking at because it's a nice blue one. But it's been bumped over to a red line when he looks at it. Yeah, so that's, yeah, that's right. What was I going to say? So SDS catalogue, what's the next slide? Oh, yeah, it's another technique for redshift as well. This is for super far away things. So that one was bright enough to get a nice spectrum where you could see a hydrogen line. But for super distant things, you've got this thing called the Lyman break. So if you're sitting next to that galaxy, then emission drops off here in the ultraviolet because energies higher than that will ionize the gas that surrounds the galaxy. Around the galaxy, you've got neutral hydrogen. Gravity's pulled hydrogen together in a galaxy to build stars and all kinds of things. And they're shining away super bright. Surrounding a galaxy, waiting to be drawn into the galaxy is neutral hydrogen. And at this point, it absorbs the light at these high energies. So the more violet you go, the higher energy it is. In fact, that's 13.6 electron volts, which is what you need to ionize hydrogen. So here we've got an extreme redshift. So redshift of 1 means it's receding at light speed from us. Here it's Z of 11. But you can't think of it as something moving faster than light. It's just that it's so far away. This is way back at 13.2 billion light years, something like that. This is from, I've forgotten now where I got this from. No, it's not SDSS. It's not James Webb. It's WISE, I think, which is an infrared space telescope. Or is it? Hang on, where's my notes? Did I get that wrong? I'm pretty sure it's WISE. But it's the same thing, same techniques that James Webb uses. That's why they built it infrared, because they're trying to see right back to the beginning of the universe. And these things are too faint to get spectra from. But what they can do is, so usually this cliff here, where the emission's really tiny, all this has been absorbed by the hydrogen around the galaxy. And so you get this real cliff here, where it brightens right up here. So usually that'd be up in the ultraviolet, but it's been redshifted so hard that there's a frame, they get nothing. There's another filter. So they take a shot in this filter, shot in that filter, a shot in this filter, suddenly it appears, this galaxy. It's not a quasar, by the way. It's just a faint, fuzzy, early type galaxy. But that's another technique, and that's why they build those space infrared telescopes. That's why they make them infrared, because all the action is down in the infrared, where it suddenly brightens up and you can see things. So I just sort of slipped that one in. It's not the technique they used to first discover quasars. But needless to say, these quasars have redshifts of, yeah, so I was going to say SDSS, which is a Sloan Digital Sky Survey, has catalogued about 50,000 quasars. And of those, 6,000 exceed Z of 2.3, up to about Z of, what does it say here? 7, 12.9 billion light years away. So there's a lot of them. And what I wanted to establish is that they're very far away. And so they're practically at infinity for all practical purposes. If you move from one side of the Earth to the other, it doesn't move on the sky. And yeah, so this is the basis of what we do with our radio telescopes. We have telescopes all around the world, and UTAS runs 2 here in Hobart, the 26 and the 12 metre. The 12 metre is the one you see as you drive up the hill to Mount Pleasant, the first one you go past. We've got a 12 metre here in Hobart, one in Katherine, Northern Territory, and one in West Australia at Yarragadee. And as today's experiment, it was scheduled months before, so they know what they want to look at. They have a sample of about 500 quasars that they use regularly because they're good and bright, they're super far away. Point source objects, no structure, you don't want structure, you don't want variability either. So they've chosen from those thousands of quasars a nice set of good astrometric pinpoint objects. Yeah, and what we do is the telescopes around the world observe these things. Remember, the Earth is moving as well. So, because it's so far away, it's a plane wave as it arrives. So, that's the signal coming in. The waveform arrives at this telescope, it arrives at this one a bit later. And we have these, the important part of it is these atomic clocks that clock the signal. So we're sampling at, say, 2 gigabits per second, and that's clocked from the atomic clock. Our atomic clocks are hydrogen masers. We've got the best clocks in Tassie. We've got a Russian one in that white container that sits outside the observatory. And inside we've got one on permanent loan from NASA. And they're both hydrogen maser clocks. The NASA one cost a couple of $1 million years ago. And the Russian one only cost $200,000. Bargain. The only trouble is at the moment we can't get the Russians to come and service it. They used to come out every 3 to 5 years to recharge the hydrogen and tweak it and look after it and check. But we can't pay them, so they won't come. So we're hoping it doesn't break down. But yeah, we need these super accurate clocks because what we do is we take the data and we bring it to a central location. We can't do it in real time because there's too much data. We're sampling at 2 gigabits per second. Actually, the other day we were sampling at 8 gigabits per second. And at each station we generated 40 terabytes of data. So part of my job is to get it to central locations, central supercomputers, and the computer, we've got a rough idea of what the delay should be between the sites because these experiments are repeated. But the computer synchronizes it. It's called correlation, which is basically shifting it by a certain amount until they line up. When they line up, all the good stuff adds up and the noise cancels out. Because if there's noise in the atmosphere or local radio frequency interference, it should be unique to each site. And so they won't correlate. The only thing that should correlate is the object in the sky. Yeah, and so these very long baselines, they're like tens of thousands of kilometers, up to that, thousands of kilometers. Yeah, like it says here, 1,000 to 12,000. So today's experiment, we had Ishioka, Japan. We had Fortaleza, which is in Brazil. We had Hartebeespoort in South Africa. The 3 Australian stations that we run. What was the other one? Wetzel in Germany. So yeah, we do heaps of collaborations like that. And so what this time delay tells us is this distance here. And so you can see that's a right angle. You can work out, given a time delay at light speed, you know the length of this side, you know the angle you're observing to your source, and so you can work out this baseline. And because of our atomic clocks that clock up to trillionths of a second, we know the distance from Hawaii to here, to Hobart, to within less than a centimetre. And especially as we repeat experiments, they sort of work the errors down too. Yeah, we also look at the GPS time, but that's not accurate enough for us because the GPS signals get delayed as they come through the atmosphere and not on a predictable sort of level. You know, the ionosphere, the upper layer of the Earth's atmosphere, attenuates or slows down radio waves. You get a sort of refraction effect. So that would fuzz it up. Back in the 60s, the best they had was rubidium clocks. And using this positioning method, the best they could get to was within 3 to 5 meters between the telescopes. But now with better clocks, we've got it down to centimetre. They're talking now about optical clocks, where they have a couple of lasers that trap an atom in a certain state. I don't understand. But if you tune the frequency of the lasers just right, you can get the atom to freeze kind of thing. You kind of trap it within a interference pattern of the lasers. But they've only managed to get that working for a few hours at a time. They can't sort of keep it hanging. But our hydrogen maser clocks are very, very robust, really. They're too big to take onto satellites, so GNSS, GPS satellites have cesium atomic clocks on board. They're a lot more compact. You can fit it on a satellite. Whereas our hydrogen maser clock's like a big blue fridge. Yeah, so it's the time accuracy that lets us measure the Earth. And so here's another animation by David. Yeah, so there's our time delay, but remember the Earth's moving, so yeah, they're at equal distance. And so we can tell how the Earth's rotating as well. The Earth's rotation varies by milliseconds every day. I think the ocean's sloshing around and things, sort of make it change. The Earth wobbles as it goes around the sun. There's precession and other factors like that too. They pick that up. And I believe we get paid for this. I'm not the businessman, but we do earn money for this for UTAS. Because Geoscience Australia fund us, because Australia wants to collaborate in this international thing, because everyone uses these data products. Because everyone's interested in super accurate positioning because of self-driving cars. You've already got self-driving farm machinery, mining machinery, robots, everyone wants to go robotic. Yeah, so when you think about the GPS system, that's a system of satellites orbiting the Earth. It's a dynamic system. Their orbits are decaying all the time and varying. The Earth's gravitational field is a bit wobbly. If you go over a mountain range, you've got more gravity than when you're over an ocean. And all those dynamic systems need this celestial reference frame based on quasars to tie everything to. So then you can see how the GPS system is varying. If we didn't do these experiments, we do them about 3 times a week, 4, then the GPS would be out by meters, tens, hundreds of meters, if we suddenly stopped measuring where Earth is with respect to these. There's a celestial reference frame, then they have a terrestrial reference frame that everything gets tied to. So yeah, if what we do seems a bit mysterious, this is what we're up to. So we're just about to, these dotted lines are supposed to represent our optic fibre links. This one's just getting put in at the moment. So at the moment, we're still shipping hard drives from here. So today, I got about a whole suitcase full of hard drives. Yarragadee, West Australia. It's about 100 kilometres inland from Geraldton, sort of just on the top of what they call the wheat belt in the Midwest. Yeah, and these are the baselines between all our elements. And that's a supercomputer centre in Canberra. We also send a lot of data to Curtin. So Curtin, they've got a supercomputer as well, Curtin University. That's a supercomputer that's going to run the square kilometre array, which is out here in the Murchison Desert. So they've already got 26 radio telescopes here, built and operating, and already doing sky surveys. But most of the high frequency stuff, dishes and things, are going to be put in South Africa. And we're going to have all the low frequency elements in West Australia. But the supercomputer's still not up to snuff yet. They're sort of hoping that by about 2030, when they have all the elements in place in South Africa, that the supercomputer will be able to handle the problem. So what they're doing, rather than build big dishes these days, they build lots and lots of little ones. So this square kilometre array is going to have a few hundred 10-metre dishes. And whenever you add a dish to the array, you don't just add one more, you add its relationship to every other element in the array. So if you double the number of telescopes, you don't just double the baselines, you square it. Or, so having hundreds of telescopes is a big computer problem. But I think they're going to be all tied together with optic fibres, so they'll be able to sort of correlate in real time. They'll be linked. Which our array at the moment, we can't correlate in real time. We have to ship the data across the internet or ship disks to Hobart or Canberra. Yeah, and where's our disks? Oh, there's a picture of our dishes. So there's Catherine, Yarragadee, West Australia, Hobart. They're all identical dishes, 12 metres. What can we say? Yeah, we've been going for 14 years now. 1,000 sessions, 24-hour sessions, so a couple a week. And University of Tasmania is funded ultimately by Geoscience Australia. So yeah, there's a close-up of them. Freshly painted, doesn't look that good at the moment. Good thing about radio is it's human scale, so we don't have to polish our mirrors and dust them like you do. As long as it's accurate to within a quarter wavelength, so about a centimetre or so, it's good enough for us. But it has got a bit of lichen on it, I've noticed. Got to hose it off and paint it again. So these ones, yeah, have sub-reflectors up here, and that's the receiver down here. And these ones, they're cooled, but they're not super cooled like the 26. So the Hobart 26 metre receiver is chilled down to minus 250 degrees centigrade. That's to keep it quite sensitive and quiet, because anything warm is radiating. At room temperature here, we're all radiating in infrared. If you had night vision goggles, it would all be glowing infrared. But we're also radiating radio as well. So a warm receiver is noisy. And warm electronics are noisy too. As you know with your cameras, you want to cool them down. Lowers the noise floor. You can see fainter things. Same with radio telescopes. Yeah, so this is our West Australia site. That's a bit fuzzy, isn't it? West Australia site, that's our 12-metre dish. And this is a NASA facility. This is a satellite laser ranger. So this thing that looks like a big telescope, it's about yay big, fires lasers up at satellites and watches for the bounce back. And most satellites have a corner cube reflector. So it's, 3 planes, all perpendicular to each other. And the good thing about that is whichever angle it hits at it, it reflects it back at the same angle, back to where it came from. And next door to us, there is the Swedish Space Corporation. And this is quite an old photo. Now there's some Japanese dishes there as well. There's about 15, 20 dishes there now. That's the Swedish one. And we sometimes borrow gear from them and they borrow gear from us. What else we got here? Oh, I've got a description here somewhere. Yeah, so that's the satellite laser ranger. It's supposed to be mobile, but it's sat there for 30 years. It's on wheels here. It's in a big sort of trailer that it lives there. And our control room's in this building as well. So this is the same as the Hobart dish. And we've also got other parts of the terrestrial. We've got GPS receivers here. And they've also got this other system called Doris. So GPS satellites transmit. Doris transmits from the ground back to the GPS. And so it's another way to tie the GPS. And the satellite laser ranger, being an optical, I think they know the height of the satellites to within millimetres. So they've got these around the world to calibrate the GPS, work out where all the GPS satellites are. Because the way GPS works, I don't know if this is too obvious, but they're sending out signals all the time at light speed, and it's your device catches a few of those and does some maths and works out where you are. But for that to work, you need to know where the satellites are. So all these systems tie together. And this is sort of the ultimate one, the celestial reference frame. And all these other ones depend upon that one. Because those galaxies are the only really fixed thing. Everything else is moving around. Yeah, another close-up of Yarragadee again. Not too exciting. You can see some dishes in the background there, the Swedish ones. Yeah, and it's just flat plain. It's also one of the sunniest spots in Australia, apparently. That's why they put the satellite laser ranger there. It's actually pretty windy there too. There's big wind farms nearby. Don't know if the wind's got something to do with it, but yeah. Lasers don't work through clouds, but radio does work through clouds. So radio is big light, 100,000 times bigger than the light you see with your eyes. And that's the reason we use it for communications, because it's hard to stop. So dust, clouds, not a problem. Keep going. This is a Northern Territory one, Catherine. They put it there because it's just out of the cyclone zone. Because our only enemy for our big dishes is the wind. So yeah, they put it there. Control room, pretty primitive generator. Every station we have a generator in case the power goes out. And up here we've got the Charles Darwin University Rural College. So it's where you go to learn how to be a jackaroo, farm skills, that kind of thing. So we just have an agreement with Charles Darwin University. Yeah, so just letting you know what we do. And here's a close-up of the dish, sub-reflector here. And so light hits a dish, focused up here, reflects off that into the receiver there. Your friend and ours, the Hobart 26. So the other one had a sub-reflector, this one prime focus. This is where the receiver's up here, prime focus. So it just sits there. Having the legs, it sits up. We know that because we had to jack it up a year or two ago to change a bearing. So it took two 200-ton jacks to lift it, plus a 50-ton jack because it was a bit sticky, I think. Just moved it up 10 millimeters so we could take the bearing out. Actually, you can't see the bearing. That's the y-axis. It was the next bearing down. Yeah, and this is our Sejuna. Not many people know we have this one. This is the Sejuna dish. So Sejuna's last stop if you're heading west before you cross the Nullarbor Plain. It's about 70 kilometres inland from Sejuna. It used to be a Telstra overseas telecommunication dish. So it was the farthest west they could go while still being plugged into the east, where they could see a satellite over the Indian Ocean, and they'd send phone calls from Europe via the satellite here, back. When you remember that international phone calls used to be so expensive in the 70s, that's why. Whoops, loose door. And this one, I just put this picture here again because this one is 30 metres across, so a tiny bit bigger than our Hobart 26. I haven't been watching the time, so let me know if I go too long. This one's also got a sub-reflector, but then it's got a tube down here, and the tube has a 45-degree mirror. I say mirror, big bit of metal is a mirror for radio, and it bounces the signal along a tube that narrows, and their receivers are in here, in this room, and that's where the axis of the telescope is too. So the tube is always into here. And yeah, it turns around in azimuth there. There's a liftway up here. And our control room's in this building here. So Telstra gave it to us. I think they were happy to be rid of it because they don't have to remediate the site. Whereas the university said one day we'll remediate the site and wreck it. But I guess there's a fair bit of scrap metal in this thing. And yeah, we've also got our High Ranger truck you've seen out at Mount Pleasant, the crane we go up in. We've got one of those here too to access the dish surface. And you can climb up into the dish surface from below as well. But yeah, there's an axis through here like that, and it turns in azimuth as well. But yeah, this one's mainly used for astronomy. It's not used for that celestial reference frame stuff, which is that kind of our bread and butter, really. And but we do astronomy as well. I'll talk a little bit about that quickly. This is our contribution to the experiments. I'm not sure, how many years is this over? Doesn't say, does it? This is just 2025. And you can see our telescopes are some of the hardest working telescopes in the world. What have we got here? That's South Africa, Germany. That's up in the Arctic Circle, Svalbard. One of our students went there to work through the winter. Koki, that's Hawaii, Brazil, New Zealand, Japan, Italy, Sweden. Oh, it's written there, isn't it? Here I am. I was trying to remember where they're. Germany again, Argentina. But there's not that many in the southern part of the world, so we're often heavily utilised. Next slide shows the stations around the world. Yeah, so we're in most of them. And this is just showing different experiments this year. So the blue ones involve the Australian radio telescopes, and the red lines are other stations. Those lines look curvy, but that's just a map projection. They're straight lines, straight geodesics between different places in the world. Just a wobbly projection. But you can see we're an important part of the whole array. I think this goes on and on and on and on. This is all the January ones. R4s, that one goes to Washington. That one goes to Germany to be correlated. That one went to Shanghai to be correlated, I think, from memory. So that's where all the nations of the world contribute. And we've got to correlate. We correlate here in Hobart too, some of these ones. Another German correlated in Bonn. Can't remember that one. Becomes a bit of a blur, I must say. So it's incessant, like every week we've got several. Yeah. So that was January. A few stats here. Yeah, generating lots of data. This is a typical sampling rate, but we can sample faster, but this one is safe. And we generate this amount of data per day at each station. A lot of my job is getting that data to a central location. Compared to like these low sampling rates, GNSS techniques. Yeah, we have to get the data from each station to a correlator, which we've got a 10 gigabit per second optic fibre link from University of Tasmania to the rest of Australia. But realistically, we get 3 to 4 gigabits per second streaming out of Hobart. So I think we're the biggest data uploaders out of Tasmania. Yeah. What else can I say? Because of the extreme accuracy of the astrometry of where these quasars are, I found this one too back in 2018. This was published. These are our people: Jim Lovell, Jamie McCallum, Staz, Lucia McCallum, and we've got, they're from South Africa, these guys. These guys are from China. Oh, he's the head of Geoscience Australia, Oleg Titov. This experiment, they looked at quasars that were close to the sun, within 1 or 3 degrees of the sun. And they're able to measure the way they moved, which was the way that general relativity was proven back in 2019. What was his name? I've forgotten now. Yeah, Einstein, but who was it? There was a movie about it, wasn't there? The British guy who believed in him. Eddington, yeah. He went out and measured a... 1919, wasn't it? What did I say? 2019. So 1919. Yeah, he did that, but this is heaps and heaps better. They managed to get the gamma, which is part of, if you're doing a general relativity equation, gamma is supposed to be 1. And so gamma minus 1, they got it down to 0.00009, within error. So they're just showing that this is using the modern, our high sampling rate and modern telescopes. Yeah, so just this kind of business. Yeah, so that's where the quasar is, and that's where it appears to be. That's there, but its light's getting bent around the sun. It gets to Earth, so it appears to be over here. Have I got that right? I think I have. Yep. 1,000,000 times bigger than the Earth, 1,000,000 times heavier, distorts space and time. This is sort of like a 2-dimensional representation of space-time. You've seen that one where you sit the bowling ball on the trampoline. Yeah. So it should be behind the sun, but it sort of appears shifted a bit. So they managed to get that down to better accuracy than anyone had done before. And I heard you guys have been talking about a trip to Bisney. So here's a picture of Bisney Tier. That's a nice high-res one. Yeah, Midlands Highway's over here somewhere, I think. And yeah, if you're down here, some places on the Midlands Highway, you can see it when the light catches the dome just right. That's a SpaceX dish. That's a 5-metre dish. That's the 0.5-metre plane wave telescope. And that's the 1.3 metre. You haven't been up there. And this one is a new one for us. We're getting into spacecraft tracking now. So this one transmits and receives. So that's the reason we stuck it up here, because we don't want a transmitter near the Hobart 26. So we stuck it up here. And yeah, so this one, they've been using that for tracking spacecraft just as they launch, and also tracking some space junk as well. I've got a little bit blurb about that. Right, yeah, what was it going to say? What is it going to... Yeah, tracking control and payload data download. Green. It's a high speed too. Fast slewing. What do they call it? Launch and early orbit phase. So they're trying to sell our services to spacecraft companies. We've also been using the Hobart 26 for tracking the Falcon Heavy rocket when SpaceX launched it. So if you've been in our control room, you'll see there's a big SpaceX rack there. So we plug that into the antenna, point the antenna at where their rocket's going to be, and then they do the biz. They're downloading telemetry and other information from their spacecraft. Because when they launch from America, it travels across the Pacific, they go west, and we're one of the first places they hit, where they can sort of find out how the spacecraft's going. You know, how the pumps are running, how the fuel supply is, that kind of thing. What was that, Steph? Oh, when they launched the car into space, yeah. The Tesla, yeah. Yes, I think they did, yeah. I wasn't at the desk for that one. I was at the desk for one where they blew up on the launch pad. So, yeah. Something like that, yeah. But usually we're at the desk, we're on the phone to Hawthorne, California, their mission control, because they want to keep in touch with us. Is everything working? Yeah, they sounded very disappointed. Okay.
And they said they were moving west.
Yep.
And then about an hour later, we looked out our balcony and there it was doing a bit of.
Okay, cool. Oh yeah, cool. Yeah, so we get, I think we get paid 20 to 30,000 per sort of every time we do a track for them for an hour or two. So it's a good earner for us, but it's cheaper for them than building facilities here. But they have got this one here that's a smaller one for their, I think it's something to do with Starlink or something like that. I don't know. There is a dish inside that. That's a weather protective radome, transparent to radio in there. This guy, we bought that from China, I believe, and it came here in a container. Tony Sprant and co helped assemble that too. There's another shot of Bisdee. I love it up there. The accommodation's over here, so you get to look out at the view. Great. Yeah, once again, that's the half-metre plane wave. And dishes. Yeah. So that's, I don't think I've covered it all. You've seen the 14-metre telescope down the hill. So that's being fixed up at the moment. We've got it moving around, and soon the idea with that one is students will be able to drive that around, even high school students elsewhere in the world be able to use that one. And yeah, I think that's where I'm at. What else can I say about things? Oh yeah, I was going to talk about some of the science things we do as well. Some of the science things we do with the Hobart 26 metre. We'll zip back to the 26. Where are we? There he is. Mapping our galaxy. So we're not, it's quite a problem seeing what our galaxy looks like because we're in the thick of it. So we use natural mazes. So you get natural mazing effects in clouds around newborn stars, massive newborn stars. So you've seen pictures of stars being born within, you know, molecular clouds, that kind of thing. Well, the brand new stars are really bright in ultraviolet, and they stimulate the clouds around, and sometimes they maze at different frequencies. Water mazes, methanol mazes are some of the things we look at. And that, you know, they've got specific lines that we know where they should be from the laboratory. By mapping them around the galaxy, we can tell how the galaxy arms are moving at what velocities they're moving. So they'll be sort of blue shifted if they're coming towards us, red shifted moving away. And I think at the Beaker Street thing, we heard that Naomi McClure-Griffiths, she discovered a new spiral arm too, didn't she, recently? A year or so ago. Or a new sort of wing or spur on a spiral arm, something like that. But we've got heaps of data on that stuff. We also look at the Vela pulsar a lot because we can track that for 22 hours a day. And a few years ago, we got a Nature paper out of that because it did a speed up and then back to normal rotation again. It's as regular as an atomic clock because it's a supermassive object. It's not quite a black hole, but it's a neutron star. Did you say someone was talking about neutron stars recently? 2 years ago. Oh, Jim Palfrey was talking about it, so yeah. Supermassive, it's like a big atomic nucleus made out of neutrons. You can't create that kind of matter on Earth. If you had a teaspoon of it here, it would disappear through the floor, straight through the ground to the center of the Earth. It's just so dense. because most normal matter seems solid, but there's heaps of space between the atoms. So in the middle of a supernova, that's what created it. You already have an electron degenerate, like white dwarf style core inside the star. And then when it goes supernova, it collapses, bounces off the core, hammers it, and compresses it even more. If it's not too massive, it makes a neutron star. If it's supermassive, it might make a black hole. So we've been watching this neutron star. When they discovered them, they thought they were alien objects because they're as regular as an atomic clock. But this one, every 3 or 4 years, at random, does a little speed up and then gets back to its regular thing. They think it's like a quantum superfluid kind of business inside in the core, and there's a crust that the magnetic field's tied to, and they sort of disconnect for a few moments. It's only a few moments, a few seconds. So we caught it in the act. So all the theorists love that, because they can do calculations about how could that have happened. And what was Jim's big news? It missed a pulse during the glitch, when it first glitched. Was one of the sort of surprising things. Yeah. So the 26 was used for that. Yeah, so that's what we do. And I've probably missed heaps of stuff. Did I say 7 telescopes? What have we got? We've got our 3 Ozscopes, Sejuna, Hobart, the 14 metre, and the 7.3 up at Bisdee, so there's our 7. Yeah. So we're pretty busy. There's only me and Brett. We've got another guy who's been away on leave for ages. And
we'll just have some questions now.
Yep.
We've gone a little bit over time.
Oh, sorry.
I think Ross is first off the rank.
Okay, just bear in mind that the answer to this question stays within these 4 walls and our YouTube subscribers.
aliens.
What I'm burning to know is, have you ever played cricket on the 26-metre dish?
No, I haven't.
I'll take the microphone off you if that's your question.
It's not quite big enough. I think you'd get away with it on parks, but yes.
All right, Richard?
Yeah, just a quick question. Do you ever have any problems with communicating with all these, because of the language situation with international
Sometimes we
facilities
get
at all?
funny English. I think the Chinese often use translators.
Oh, right. I just wondered how you all managed all that. Yeah,
But I think a
it's
lot of those
complicated.
people, they learn English because
It's a lingua
most
franca.
lingua franca, if you're
Yeah.
writing a paper,
Yep, yep.
you want to have some sort of basic English. But yeah, sometimes with technical things, you've got to like repeat things a few times to make sure you
Yeah.
get it right.
Yeah. Interesting.
But we are talking to the Germans, the French. So sometimes you get some funny kind of English.
Hi there, you've got massive data. Do you have lots of internet and all that sort of thing, or do you have those hard drives
Well, we've got
and you
a
mail
few
them?
petabytes of storage here in Hobart. We've also got a new data centre in Cambridge that the university runs, and we're one of their big customers. And like I said, we've got a 10 gigabit per second. That's the Australian academic and research network that links all the universities and big facilities around Australia. But practically, we get 3 to 4 gigabits per second streaming the data when we're sending it off to the correlators. Yeah. That's a lot. It still takes a day or two to send 10, 20 terabytes.
All right, down the back.
It is a big problem.
Warren, at your first slide where you were talking about the
Quasar.
that red jump in the red shift
Oh,
that
that
was
one,
discovered in the 60s by Schmidt, Martin
This is
Schmidt.
a more recent technique for
yeah,
space.
but in the
telescopes
first
infrared.
slide,
next one,
where
yep.
you said that they'd picked up a change in that
Yeah.
where it had changed the
Gone from like
redshift.
480 to
Yeah,
600.
what was the significance at the time of that discovery?
They were just very shocked to find such a thing that looked like a star was so far away. It was this one. It just looked like a stellar object. And that's why I had the first slide too, because that's what it is. That's a star, that's a quasar. Yeah. Until you get a spectra of it and work out how far away it is. I mean, back in the 20s, they were shocked to find galaxies were like, hundreds of millions of light years away. Yeah. The distance was a big shock, yeah. And for such a compact object, such a bright object, because distance means if it's that bright, it has to be, like I said, a trillion stars luminosity. And then they realised it's in a compact area. It's only like maybe a light month across. Whatever that is. Yeah. I think that equates to about less than a parsec, less than a couple of light years. It's a parsec, 3.2 light years. So that kind of, pretty compact zone in galactic terms. Yeah. So that was the shock, that it was so bright, it was so far away. Yeah. Yes?
Yeah, are you involved in plate tectonics? Because you're measuring the distance between your stations.
Yeah, so we see Hobart moving northeast 4 to 6 centimetres every year towards Hawaii. There's a whole Australian continent's moving. Yeah, well, we are moving northeast actually. And I think the plate's also rotating a bit too. I'm not sure which way. So originally in the 60s, 70s, they were like figuring out where these galaxies were and how far they were away. Then someone realised that, it keeps changing here on the ground. So then, because tectonic plates used to be based on fossil records and geology. In fact, I read the other day, part of Western Tasmania used to be associated with the Grand Canyon or something. Like way, way, way back. Some of the rocks are similar.
Professor Warren Hankey used to teach us geology. He never saw up in the level.
So, yeah. And I think there was an earthquake in Japan when one of the telescopes suddenly went down 2 meters, like overnight kind of thing. Because, plates subtending on other plates, and one of those big earthquakes in Japan, everything just... The Earth's crust moves by up to 20 centimeters a day in places around the world. Because you see the oceans move, but the crust of the Earth is flexing with tides, just tidal flexing. In fact, I think the Earth's crust still rebounding from the last ice age too. It's just very slowly, millimeters. So it had ice weighing down it. Now the ice has melted. I don't know, what was that, 10, 15,000 years ago? So the crust is rebounding just gently from that. Yeah, very subtle stuff they can pick up.
One last question? Anyone? Renee?
Yeah, Renee.
You said that the clock that the Russians were fixing, we can't pay them to come and fix it anymore. Why can't we pay them?
I think the Ukrainian war. I think there's embargoes on
So it's just
paying bill. We can't pay the bill.
yeah.
We're not allowed to. I don't know. I'm not in the business side of it, but that's what I understand. So we've got our fingers crossed that the war ends and we make friends again.
Did you have a question for Warren before I did?
No, after that last one.
Oh, I did run for over. Oh, sorry.
No, that's
Ran a long
fine.
time. Sorry, guys.
So Warren, that was a fascinating talk, and we love seeing science being done and done locally, and you're really using that equipment out there to its fullest potential, I think, and that takes a lot of work. So we're yes, thank you.
I think we're punching above our weight.
Yeah, well, I'm
basically, so.
definitely punching above your weight, and when you saw that, the maps and the linkages always coming back to Tasmania, that was terrific. So,
Yeah.
and you're full of interesting facts. So, there's some lovely information coming out through your talk. So, on behalf of everyone here tonight, we really would like to thank you for your
thanks, Russ.
presentation.
Cheers. Cheers. Cheers.
And a little
Thank you.
gift on.
Oh yeah, he knows what I like.
Oh, double.
Thank you. And I just want to say about Astronomical Society in Mount Pleasant. I mean, the whole purpose of that Great River Museum is to promote astronomy and that kind of thing. And that's what you guys do. So we're more than happy to cooperate and work alongside you guys.
Yeah, thanks. Thanks very much, Warren.
Cheers,
and
thanks.
you had that lovely photo of Bisdee Tears. I hadn't seen that one before, so it looks very nice.
Yeah, they're
up
good
there.
ones. I think
It is.
Giffray gave me those ones.
Bryn Emptage at UTAS,
Yeah, that's good.
he asked me to contact him early September to find out whether it was possible for us to have a trip up to Bisdee Tears. So just stay tuned. Hopefully we can organise something this year, if not next year.
Yeah, it's only about an hour away.
It is,
from Hobart, so.
yeah. And we're hoping to involve our northern members as well, so allow them to come down. All right, well, we're going to have supper now. If you haven't filled in a ticket for the Lucky Door Prize, please do so. It'll be drawn straight after the break. So, thank you.
Sorry, I went over time. Oh, Mike? Yep. Oh, there's the,
Enjoy your cup of tea.
the wind
No,
socks
that was
elephant.
really great, Warren.
Okay,
Yeah,
thank
that was
you.
You're right, I'll sit down.
Thank you.
brilliant.
Okay.
Yeah, you're right.
Is it on? Yeah. We'll kill some lights. Okay, folks, well, a quick tour of the night sky in September. This is set at 15th of September. Hopefully it'll begin with a, as it should do. Oh, that's positive. Just setting the tone. I know it's the same every September, but I've updated a few things. So as we look north, it's an exciting vista at the moment. All sorts of constellations, and I'm going to focus on a few of them in particular. Now, you know you've got the Messier challenge that's been going on, thanks to our Presidente, who set that up and running. So we're looking at the centre of the Milky Way at the top left there, Capricorn, Aquarius, Aquila, Vulpecula, Cygnus and Pegasus. These are the things I'm going to highlight for you in a moment. First of all, that star, Altair. Now, none of us really look at individual stars, but it's a beautiful star. And it's only about 17 light years away. And an A-class star, so it's blue-white, but mainly more white than blue. And it's a really good, if you're going to set up for those of you who do astrophotography, because it's close to the celestial equator, it's really good to do your guiding calibration with that star somewhere in the field. There are lots of other nice stars around it, but it's a great way to start. Works for me anyway, so Altair is a good one to begin with. Vulpecula, of course, is home to the Dumbbell Nebula, which some of our members have been imaging lately. And so I'll talk briefly about that. And Steve's familiar with this beautiful double star, Albireo. Well, it's a triple star, really, because it's got a close double and a blue star as well. So it's a very pretty star to look at through a telescope. So some of these targets are good for observation, some are good for photography. And of course, the great Pegasus cluster up there, and that little mysterious object, which we all know as the Helix Nebula. And some of our members have been photographing that lately too. Absolutely ideally located at the moment in the northern sky, eastern sky. Now, I love this object, only because roughly a week ago, I started imaging it for the first time, and that's can people know what I'm talking about there, the two parts to it? This is the Cygnus Loop, Cygnus Loop. It is a spectacular supernova remnant to photograph. The only problem being the Western Veil and the Eastern Veil, the two main parts, but there's a third part as well. The problem is it's low down, as you can see. It's in the northern hemisphere. So we're looking through all that murk, through all that atmosphere. And so that's a problem from a point of view of even observing, let alone imaging, because you're looking through more atmosphere. So it rises to a height of about 16 degrees as it culminates, crosses the meridian. But so far I've got 2 hours. I'm so excited. I've got 2 hours and 20 minutes of data on this object, and I'm not processing it. I'm waiting until I get about 5 or 6 hours at least before I process it. There's a lot of stuff going on there. It's a really, really beautiful thing to look at. But let's look quickly at this wonderful object. Now, the Dumbbell Nebula, some of you may have, has no one observed that through a telescope, just observed it. The magnification is still pretty small, but of course the more magnification used, the worse it is. It gets dimmer. It's not, it's a trade-off, isn't it? You lose the brightness. Now down here, there's Albireo, and a beautiful object, a triple star, 420 light years away. It consists of a bright giant, which is a binary, so it's got a little. Have you ever seen the other star next to it, Steve? Just, I know you're an avid observer. Yeah, I think they're very close too, because the orbital is something like, it doesn't tell you there. Yeah, it is 121 years between the binary component. So they're fairly close together. And the third star, the outer star, is a beautiful blue star. So you can see the colour there in that picture. That is worth searching out in your telescope. And there's a gorgeous picture of it, bottom right there, through a reflector. Now, looking north again, a couple of things. Let's concentrate just briefly on Capricorns, because there's one thing there of particular interest. M30, now here's our Messier chase again, that beautiful jellyfish cluster. Now, did you find this one? Was that on our Messier list at all? No, M30 wasn't. Size. So worth searching that out. If you look up at the ecliptic, come along to Capricorn and you'll see it there. A very pretty little cluster. It's got an amazing density, 150,000 stars, but about 1 million times per cubic parsec. So the centre of that is incredibly dense. I don't know how it would compare, say, to 47 Tucanae and others, but that puts it at a very dense core. And it says here, there are lots of binary star systems in it, and blue stragglers are produced as a result of the proximity of those stars. So, and there's I've just done a little stellarium thing, of 171. So even then, it's very small. But if you've got a larger aperture telescope, you probably get quite a nice view of it. Now, we've also looked at this area. Last views, well, not last views, but because Milky Way is gradually heading west and sinking in the western sky of an evening. But Sagittarius is still worth exploring for the Lagoon and Trifid nebulas. And down here, yeah. Anyway, there's a beautiful shot by an astronomer by the name of Ken Crayford. Lovely, with the Witch's Broom. Spectacular object, really. I like those bits of complexity in the gas filaments. And there are a couple of ideas of what it would look like through binoculars, but you wouldn't see much, of course. No. Just to give you an idea of the size of the object, though, it's several degrees across, so 3 degrees or more. So it's quite a prominent object to look at. Anyway, let's leave that and move on. Now, Saturn. Anyone looked at Saturn? We looked at Saturn on Saturday. It was a lovely object, came up rather late in the evening, but the people just squawked they were thrilled to see Saturn through a telescope. And it was a very pretty sight. And we saw them through 2 telescopes at the wharf, which is amazing down there because, the pollution's terrible. But we were able to have a good look at Saturn, and it's worth looking at. So this is what you'd see on the 15th at 9 o'clock. We noticed, I think we saw, Michael, we saw Titan, didn't we? I think we saw Titan. We managed to spot Titan, not the other moons, but certainly Titan and the planet, of course. So watch out for Saturn at the moment in our skies. And over here, that's my shot of, reduced size, shot of the Sculptor galaxy, NGC 253, which is a beautiful galaxy to photograph. And that was with a 4-inch telescope. So, yeah, it is amazing. It's a beautiful thing, and it's quite big. At 27.5 arc minutes, it's almost the size of the moon. So, and it is bright. It presents quite a bright disk. You can't miss it. So any telescope will be useful for looking at that. Another shot, that's just a model of it. That's using 117 magnifications. That's quite a bit, but and that one there is 34 magnifications. So in a low magnification, you get a lovely bright image, be worth looking at. Now up here, a couple of interesting galaxies. Now I know this is dear to the hearts of a few of us who have been imaging these. The top one is a really big one, NGC 55, the String of Pearls galaxy. Eugene, you've been taking pictures. Greg England, of course. I'll show you one of his pictures. It's amazing. And the one down here is the Sculptor galaxy. Now, as I've said before, I think, in Stellarium, it's called the Southern Pinwheel, which is wrong. Which is actually called the Sculptor Pinwheel, because the Southern Pinwheel was M83, which has nothing to do with it. So if you see that, don't worry, ignore the name. So Sculptor Pinwheel, beautiful, beautiful galaxy. I'm going to show you some photos that people have taken of those from our society because they're worth looking at. I think that is one of them. Now, 6 million light years away, magnitude 9, 94,000 light years across. 22 light minutes across. It's quite a size and a lovely galaxy to photograph. This is an idea of APS-C sensor and the telescope there's a 9 1/4. So Eugene, in your 9 1/4 celestial, who else has got a 9 1/4 celestial? Have we got only one in the society, or yeah? So it's big. It would fill the front. Yeah. Yeah. Yes, which is a lot of focal length. Yep. Now here's the string of pearls. This is the bright string of pearls galaxy. Very long, 32 by 5 arc minutes. And remember Robert Burnham's Celestial Handbook called it one of the outstanding galaxies of the southern heavens, and it is beautiful. Now that's a picture. I don't know. I think that's either Wiki Commons or Wikipedia. It might be a Hubble image. I'm not sure, but I will show you in a moment Greg's image of it. And that's a view through at a magnification of 30 times. So worth looking at. So both those galaxies, keep them in mind. They're really good targets to look at. Now this one here, yeah, that's with the Celestron again. Yeah, wow, without the reducer. Okay. Right. Greg England took that photo. Isn't it stunning? So he manages to, you look at his photos and you look at Hubble images and other, you think he does a good job with a thing that costs, hundreds of dollars, not billions. So that's an amazing photo. And that I think is La Silla Observatory in Chile. Took that photo. And that's a 2.2 meter telescope, not an 8-inch Maksutov Newtonian. Anyway, yeah, so sorry, that belongs to the last slide. Now, this is Lisa's wonderful shot. Where are you, Lisa? Well done. She's sitting up. Yeah, beautiful. This is NGC 300. What a gorgeous photo. And Greg's photo of NGC 300 as well. Both just lovely, lovely photos. And that is, again, the La Silla Observatory. So you can see amateurs do a pretty good job compared to for bang for buck, as they say, for the size of the telescopes we use. We're doing a good job there. Now, just looking down here at Fornax. Everyone knows where Fornax is, in the southeast. This is a magnified view of Fornax. Now, this is a beautiful place to go with your telescope, with your binoculars. Lots and lots of galaxies. The Fornax cluster is what it's called. And down here is one of my favourite objects, which I want to take a photo of. This is the Great Barred Spiral in Fornax. And it's got two huge arms on it. And I'll show you, there's a close-up view of it by Hubble. But it is one of the most spectacular galaxies, but it's small. And that's the thing with it. So I've got a small camera with a small sensor to give me a little bit of extra boost in terms of focal length, so to speak, even though it's not literally a change in focal length. But to photograph that, you need the magnification. You do need something that's fairly... So this is 11 by 6.2 arc minutes, about 200 by 306,000 light years across. It's also called the Fornax Propeller Galaxy, for obvious reasons. Yeah. But wow, upcoming target, and that's from Hubble, I think, that there's the centre of it. And then on the left there is just a frame up using the camera I've just bought, Big Bertha refractor, which will give me that size image if I ever get around to taking a photo. And now this is a interesting, now guess who took that? Greg England. Now if you go online to look at that galaxy 1269, which has also got another catalogue number, 1291 as well, it's a ring galaxy, but if I enlarge that, you'd be amazed at the quality of that photograph. It's astounding because it's so faint and so small. 33 million light years away in Eridanus. So if you go to the Fornax group and move up to the right, there you've got this lovely, lovely galaxy. Is that the one that's called the Snow Collar? It might be. I'm not sure. And there's a picture by, now these, of this particular galaxy down. These are colliding galaxies from Chile, 26 hours. using a CDK, so a plane wave, 1 metre plane wave instrument. You can see how faint some of these things are. And there's a frame up of it. So 1316 is another one to look out for, right in the middle here, just above the part of the Fornax group. So they're probably some of the most interesting galaxies there. They look like they're merging or interacting anyway. So for those of you who want to do any photography, it might be worth pursuing those. Now, there's the Fornax A cluster framed in Takahashi. Just to give you an idea, that's about 3 degrees. So you could do the whole group, you know, the whole cluster. This reminds me of, what is it, Macarian's chain that we've looked at. The same sort of thing. You can get a cluster of galaxies in. Some elliptical. There's 1365 right in the middle again. One we were just looking at. Very nice to scan over that with your telescope and have a look. Now, just moving south, just quickly. I'm sorry I'm speeding up. Richard's technique for finding the South Celestial Pole. No, you've probably heard this before. Just find Canopus and Achernar and make a triangle roughly. It's not really equilateral, but it's near enough to a good triangle. So you can often find the whereabouts of the South Pole that way. Of course, they're circumpolar, so there's no problem. You just take into account their rotation. So that's one quick way for those of you who search for the South Celestial Pole, as we constantly do, even roughly. And then in the middle of that, well, the Large Magellanic Cloud and the Small Magellanic Cloud also form a nice triangle. So now those things are darn faint. And even at Mount Pleasant, we've had nights where we can't see them very well at all. And I don't know whether it's light pollution that's got worse, but it's increasingly difficult to spot them with the naked eye. Yeah, and I think it's Sorel, and you know, you look over there and you look to the south and you think, oh, where are they? And they should be up there. And finally, like last week we spotted them, but yeah, sometimes they're devilishly difficult. Oh, just doing a bit of circumpolar rotation there. That was just a gratuitous graphic to make you all dizzy. Let's move on. I think I used that slide in the Night Sky Explorer course somewhere, didn't we, Steve? I think with the rotation. Now, I know things are down low on the right, but let's look up here for a moment. Look at this area of Hydrus, and then we'll go down to the right here, because looking south, because there's some very interesting stuff going on here. So, and this is very close to the South Celestial Pole. 47 Tucanae, still a beautiful target, by the way. At the top left there. There it is, at the top right, I mean. And of course, the Small Magellanic Cloud. Now, the Small Magellanic Cloud is, yeah, fuzzy, elusive, but worth having a look at if you can look through a pair of binoculars and gather a bit of light, preferably from a dark site. So NGC 292, 200,000 light years away, and I think it's got 3 billion stars in it, from memory, something like that. And this is a 7 by 50 binocular view. So you could fit the thing in there quite comfortably. And that's a picture I took only very recently. That's a work in progress. That's only very little exposure time. And I've boosted as much as I could out of it. But the interesting thing about it is all these beautiful red areas of nebulosity all the way through it. I don't know what that star is on the left. I have no idea. But sorry? And a couple of globulars, yeah. It's an interesting object. So I'm still photographing that. So now let's have a look down here. Don't give up just because it's low. Swinging through Hobart and Sorel at the moment at 9 o'clock in the middle of September. You've got Crux and Corinna there. In between them, down south, you've got Vela. And framing all that is this rather interesting area here, which we always sort of go to with Eta Carinae and so on. I'll just show you. So let's have a close-up look at this. Now, we're familiar with most of these things, you know, 3532, the Wishing Well cluster. You've got Eta Carinae. Over here, you've got the Gabriel Mistral Nebula, and you've got this, and the 3293, which is a beautiful, the Gem cluster. And over here, if you look, you can see, you can make out the Statue of Liberty Nebula, the Running Chicken. So all of this is worth exploring. Don't give up on it. Just get your glasses, your binoculars, and have a look at this, because it's a beautiful part of the sky. I think it's probably the best part of the sky, actually. The wonderful Southern Pleiades over here. So now, and what? And the nova is down the bottom. Now there are a couple of, I just want to concentrate on a couple of things that you don't normally look at. So the Southern Pleiades is beautiful. A picture I took recently. I just love the Southern Pleiades. Through a telescope, you won't get the background hydrogen alpha. You won't get that, but you will get the beautiful. The self is spread out but striking. It's really pretty. So watch out for that. Now just go up, depending on where this is going around the pole, up from Eta Carinae. You can't miss it, the Southern Pleiades. Now, another interesting object is the one that no one ever looks at and talks about, and no one ever takes photos of. And in fact, there are very few photos of it on the internet. This is the hand cluster, NGC 3114, and it's got a funny starfish. I don't know where they got the hand cluster from, but it's got a really funny starfish type pattern to it. And I did take a refractor shot of it, but I'd love to take one through a reflector, get some diffraction spikes, and maybe a slow reflector might be better so you don't lose, the form isn't lost in the background stars, because the longer you expose for, of course, all the other stars come out and then you end up losing that lovely pattern. So watch out for that, the hand cluster. And in fact, Stellarium's the only app I've ever seen that name in. It hasn't got a name otherwise. So that's one to look out for. And over here, now this is something I didn't really notice. 3572, now if you look up here, 3572, around here we should have, I can't see it, 3576 is superimposed. You've got the Statue of Liberty, and over here, no, that's all I want to. Yeah, over here in the middle of all this is this, is it V or Gamma Carinae? Have a look at this. There's this amazing object. Now, I haven't seen anyone take any photos of this, Southern Tadpoles, at least not so wide field. So I'm looking at this cluster here. This is the 3572. That's the actual cluster. But beneath it is all this fantastic area. So I really recommend someone do some photography of that. I'm going to have a go at it because it looks so fantastic. That is a really interesting object. So Carlos Taylor got the APOD for that image, APOD award, which one can only dream of. Now, just quickly to finish up, we just headed west. Now, your last chance at Scorpius. Scorpius is setting, and of course, along with it, a Ophiuchus. You've got a Ophiuchus. You can see now the galaxy is starting. This is at 9 o'clock. The galaxy is already starting to head in a westerly direction, because of our orientation, position around the sun. So now, at that time of year, this is your last chance to do anything over here and do some photography. And so, if you look up here, I want to show you this beautiful cluster, Caldwell 76, which we looked at the wharf on Saturday, and it was spectacular. Michael's Maksudov Newtonian. We looked at this beautiful cluster, the Table of Scorpius cluster. Yep. Did anyone see that? That is beautiful. And through a telescope, sorry, this is the stars next to it. I'll talk about that in a minute. Through a telescope, the cluster, which is right there, I'll talk about these stars in a minute. I'll come back to that. The stars there are in a kind of like a small, they call it the baby crocodile cluster. But when you look through a telescope, it has a beautiful form, but when you take photos of it, it disappears because all these other stars take over, and the cluster, there are stars that you don't see through a telescope that come out. So Table of Scorpius cluster, 2 to 7 million years old, beautiful blue, striking blue stars, and 15 arc minutes across. Now, just pause for a moment. On the right there, Zeta 1 and Zeta 2 Scorpii are at the top of the Scorpion stinger. Now, I've turned this 90 degrees clockwise because you just saw Scorpiuses like that. So I've just turned the tail that way to show you a couple of things. So the two stars there in that orientation are amazing. This one here, the bright one, you've got a bright one and a slightly not so bright one. The brighter one is Zeta 2 Scorpii, and it's a K-type star, and you can actually see a little bit of colour there. You probably can't from back there. And that's 133 light years away. This one, Zeta 1 Scorpii, is almost as bright, but it's 5,000 light years away. So 40, 50 times further away. So what does that tell you about the one that's further away? It must be a very big star, and it is. And it's they reckon it's a hypergiant. So that is amazing. So when you look at that's a good illustration of the inverse square law, and all the stuff we talk about when you see stars so far when they're almost as bright as each other, and it tells you a lot about the more distant, the luminosity of the distant star. There's the cluster that I'm talking about. So the table of Scorpius cluster. This is not upside down. It's right way up, but I've turned that around. So just quickly, the Prawn Nebula is right next to it. Now, I am stumped if I can ever see a prawn. But some images of the prawn actually look like a prawn, but other images, the longer you expose it for it, I'm going to show you my image in a moment, and I can't see a prawn. Emission Nebula, this is a good image of the prawn, if you want to see the actual prawn. Now, that one was, again, the La Silla Observatory, ESO La Silla Observatory, so that's an 8.2 metre telescope. I don't know whether they used that. They've also got a 1.8 or something, 1.8 metre. But if you look at that, beautiful, and you can see the two eyes of the prawn. Can everyone see a prawn? No. Anyway, it's a bit of a stretch. So I took a picture of it only a week ago or so, and look, where is the prawn? I can't see a prawn, but down here, there are those two eyes. So you can see in that nose bit. And there's the table of Scorpius cluster up here. And above and out of sight, just out of sight are Zeta 1 and Zeta 2 Scorpio. So anyway, I can't see it. I tried my best, but it just didn't work. No prawn. Lobster, yes, but prawn, no. And now I just want to show something for those of you you're keen on understanding where we are at the moment. We're down here. Here we are. This is a solar system. Here's our galaxy. We're coming into spring. So we're coming around here in our orbit. And we are, as you can see, the Milky Way is setting. So it'll be up there during the day. By the time we get round to summer, the Milky Way will be crossing our sky during the day, not at night. So you'd have to wait till the wee hours of the morning to see anything come up at all. So what does this mean? Well, we in summer are going to be on that side of the sun and looking out. And what do we look out at? Orion and all that area where there are fewer stars. So we're looking out of the galaxy, not into the plane of the galaxy. That makes sense? So that's all I want to say about that. So to explain the weirdness of where the galaxy's gone all of a sudden. That's it, folks. Just a quick, sorry if I kept you a bit long, but there are things to look at, and I will refer to some of them maybe in the newsletter. People coming newsletter. No, Bill. There's YouTube. Sorry, yeah. Any questions, guys? I tried not to deal with the regular things because we always look at the same things, but some of those things, like the hand cluster, are worth looking for. They're very pretty. Yeah.
Actually, the M23, I just had a look. It's actually within the Milky Way, which is unusual for globulars. Yeah. M22, the Sagittarius cluster. No, the 10,600. Yeah, it's a globular. Globular. Yeah. That's within the. Yeah. It's very. Well, it's a close globular. Yeah, very close globular. Yeah, I think it is the closest one. Yeah. Mm. All right. Thanks very much, Richard. There's no questions.
Sorry, it's quick.
So we'll just finish up with a reminder of next month's events. We've got the members astrophotography workshop September the 23rd. There's a members observing night September the 27th. So we now have 2 6-inch Dobsonians, 2 8-inch Dobsonians for use. So plenty of telescopes to go around. Come along to those observing. On the September the 30th, we have Kelly Clitheroe from Geelong. She's a member of the ASV. She's going to be talking to us about astronomy in the classroom and outreach, which I think is going to be interesting to a lot of us. So that's September the 30th. So I hope you enjoyed tonight, and we'll see you soon.
Oh.